This is part 2 of the Chapter 19 lecture videos. There will be a tiny bit of new content in part 2, but the majority of this video is to practice using the information that was discussed in part 1, which is to identify the electron domain geometry and the molecular shape of a Lewis structure. That could also include figuring out the bond angles. If you have not already done so, grab the Vesper VSEPR handout found in the Chapter 9 folder in Canvas. Once you have it open, the title at the top of the page looks like Electron Domain Geometry, Molecular Shapes, and Hybridization. That is where I put pretty much the information from video 1 in one handout. It's not a very short handout. It's like 5 pages long or something like that. But it's got the information that we need. So if you look at the Chapter 9 notes that I had posted, these are not necessarily the same Lewis structures. I added some, changed some out. What I have in the slides and what I normally do in class on the whiteboard are pretty close, but usually I add a couple extra ones in. So we now have 7 examples. So we're going to go through all 7 of these structures. We're going to draw their Lewis structures. Then we're going to identify their electron domain geometry, their molecular shape, and their bond angles after we draw their Lewis structure. So we're going to start with ClO2-. So step number 1 is for us to draw the Lewis structure. So we have to think about Chapter 8. And in Chapter 8, we had a set of rules that we followed to draw the Lewis structure. Step number 1 was to add up the valence electrons. So there are 7 electrons in chlorine. There's 2 oxygens, so 2 times 6. And the -1 charge is going to be an extra electron. So we have a total of 20 electrons in our Lewis structure. Next is to find the least electronegative element and put it in the center. If we look at the periodic table, fluorine is the most electronegative element. And oxygen and chlorine are actually both right next to it. In this case, we're choosing chlorine as the central atom because there's only one of those. They're like kind of equal in terms of electronegativity, so there's only one. So I'm going to put chlorine in the middle. Then I'm going to attach the oxygens. Next rule, so I've used 4 electrons so far. Next rule is to fulfill the octet of the outside atoms. So I have used 12 electrons, so I'm at 4 electrons left. Next we need to look at the central atom. Right now the central atom only has 4 electrons around it. It needs to have 8. Well, we have 4 electrons left, so I'm going to take those extra 4 electrons. Trying to make happier dots. There we go. And we've used 4 electrons, so we're now to 0 electrons. So we need to look at our Lewis structure. Every atom has its octet. We've used all 20 electrons. We should double check with formal charges. I'm just going to kind of say it out loud. So oxygen, formal charge, I guess I'll write it up here, just a reminder, is the number of valence electrons minus the number of dots plus the number of lines on that atom. So for the oxygen atom, 6 valence electrons minus 6 dots and 1 line minus oxygen, 6 valence electrons minus 6 dots and 1 line, so -1. And then chlorine, 7 valence electrons minus 4 dots and 2 lines. That would be like a +1. Okay, so formal charges aren't great for this one. We knew that they weren't all going to be 0. So what we can do now is check to see if chlorine can violate the octet rule. Is it in the 3rd row? And the answer is yes. So what we can do is if it violates the octet rule, I'm going to move 2 of the electrons on this oxygen over here to make a double bond. That's going to change the formal charges for both this oxygen and the chlorine. So it now has 4 dots and 2 lines. When we do this, the central atom is the only one that can break the octet rule. The outside atoms can only have 8 electrons. So 4 dots and 3 lines, that's going to be a 0. Okay, so here is our correct Lewis structure for ClO2-. Now, if you look back in the notes, we actually did this one in Chapter 8. We did it at the beginning of Chapter 8 before we had learned about the octet rule, so we had left it the way it was before. So we've got our Lewis structure. Now, I want us to find the electron domain geometry, the molecular shape, bond angles, and I guess I should have put this at the top, the number of electron domains. So to figure out the number of electron domains, we find our central atom, which is chlorine, and we count. Every single bond counts as one electron domain. Every set of 2 dots counts as one electron domain. Every double bond counts as one electron domain. And every triple bond counts as one electron domain. So electron domain, electron domain, electron domain, electron domain. That double bond still only counts as one electron domain. So there are 4 electron domains. So if you've got your handout, the electron domain geometry, molecular shape, and hybridization, what you're going to do is you're going to turn until you find the heading that says 4 electron domains. So on the front page it says 2 electron domains and then there's stuff, and then 3 electron domains. So I'm going to go on the back of the front page. 4 electron domains. It says below that, electron domain geometry is tetrahedral. So all you have to know to figure out the electron domain geometry is the number of electron domains. Next it says molecular shape. So this is where we need to look at what type of electron domains are they. So there are 4 of them. Well, the 2 of them are bonding and 2 of them are non-bonding. And I know that because bonding ones are either single bonds or double bonds or triple bonds. And non-bonding ones are the sets of dots. So if we look at the scenario, 2 bonding and 2 lone pairs, which are non-bond, it says the molecular shape is bent. Okay. And in the bond angles, it says less than 109.5 degrees. So a typical tetrahedral electron domain geometry would have exactly 109.5 degree bond angles. But when we start adding these non-bonding electrons, these lone pairs, those bond angles get smushed because the lone pairs take up extra space. Okay, so PF6, -1. We're going to draw the Lewis structure and then answer those same questions. So I'm going to get a little quicker at doing the Lewis structures. I might not talk out every single part of it. I'm putting, these are not coming out very nice. Those, the fluorines, each fluorine is supposed to have 6 dots around it. Okay, so I have used 2, 4, 6, 8, 10 with the 10 electrons from the lines. Right, yep. And 2, 4, 6 times 40. Hold on. Create. Yeah, no, okay, we're good. It's because it was 8 is what it was. It was -8 for the bonds. There we go. And then it was 40 electrons for the dots, 40 dots. Okay, sorry. That math was not working. So let's figure out the number of electron domains. I'm going to write ED for electron domains. How many electron domains do you think are around the phosphorus? Well, I count 6. So if we look at our handout, we keep turning until we get to 6 electron domains. That's going to go a couple more pages in. 6 electron domains. The electron domain geometry is octahedral. The molecular shape. This is where we need to look at the number of bonding and non-bonding. Well, there are 6 bonding electron domains, 0 non-bonding electron domains. So the molecular shape is also octahedral. And the bond angle is 90 degrees. Okay, next. This one's going to look a little bit more exciting. We've got a little bit more fun now. So adding up our electrons, 8 for the xenon, 6 for the oxygen, 7 for each of the chlorines, so I get 42 electrons. Xenon is in the center. Put an oxygen and 4 chlorines around it. It doesn't matter the order, like where you put the oxygen compared to the chlorines, as long as all of them are branching off of the xenon. Now, if we counted up our electrons at this point, we are 2 electrons short. We have used 40 electrons, and we have to use exactly 42. So I have to put 2 electrons, oh, I zoomed in, on the xenon. And the reason why they have to go on the xenon, because the outside atoms cannot have more than 8 electrons. But the central atom, xenon, is far enough down in the periodic table that it can violate the octet rule. Let's check formal charges. So formal charges for chlorine, 7 valence electrons minus 6 dots in one line. That's a 0. I'm going to put a 0 in all the chlorines because they'd all be the same. Xenon, 8 valence electrons minus 2 dots, and right now, 5 lines? So it'd be a +1. And then oxygen is 6 valence electrons minus 6 dots in one line. That's a -1. So +1 and -1 isn't the worst, but I'm going to see if I can try to fix that. So what I'm going to do is take 2 of the electrons from the oxygen, and I'm going to have it share them with the xenon, and then redo formal charges. So now it's 4 dots and 2 lines, that's a 0. And then xenon would be 2 dots and 6 lines, that's a 0. So there is my correct Lewis structure. So, number of electron domains. We got to look around the xenon and count how many electron domains there are. 1, 2, 3, 4, 5, 6. 6 electron domains. So electron domain geometry is octahedral. Molecular shape. This is where we need to look at the type of electron domains. We have 5 bonding electron domains and 1 non-bonding electron domain. So when we look on our handout, that molecular shape is square, pyramid. Bond angles. They are mostly 90 degree, but they'd be a little bit less than 90 degree. There's also going to be a greater than 180 degree bond angle. So something that you may or may not have noticed, when we draw our Lewis structures, we're just putting the atoms in the dots around the central atom. When we're finished drawing our Lewis structure, they don't usually look like the actual molecular shape or the electron domain geometry. That's why we have to count the number of electron domains to figure out what they would look like. If it's something that's going to bother you, you could redraw this if you wanted. I am not forcing you to do this. But if you wanted to redraw it to where it looked closer to the real shape, this is what it would look like with the dots around the chlorine. So these 4 chlorines would be flat on the ground in kind of like the shape of a T, with the double bond to an oxygen pointing straight up. Okay, let's go on to PF3. 5 for phosphorus. That's not a number. 3 fluorines times 7, that's 26 electrons. Phosphorus goes in the middle. Put my 3 fluorines around it. Count my electrons. 20 minus 18, 2. So I'm going to put the last 2 on the phosphorus. If we check formal charges, fluorine 7 valence minus 6 dots 1 line, so 0, 0, 0. Phosphorus 5 valence minus 2 dots and 3 lines is a 0. Glorious. Okay, so the number of electron domains around phosphorus. There are 4. 1, 2, 3, 4. So its electron domain geometry is tetrahedral. And I know that because it has 4 electron domains. Its molecular shape. This is where I need to look at what type of electron domains are there. There are 3 bonding ones and 1 non-bonding one. So that is trigonal pyramid. Now, I do want to warn you, there's a lot of, or a few anyway, shapes, molecular shapes, and electron domain geometries that start with trigonal. There's trigonal planar and there's trigonal pyramid. These are not interchangeable, these are different. So it's important that the second word is also important. So the bond angle is going to be less than 109.5 degrees. Everything that's tetrahedral is around 109.5. Once we start introducing lone pairs like the dots, they get less than. So one lone pair is 1 less than 109.5. Okay. We've got some antimony and some chlorines. So got 40 electrons. SB goes in the middle. Chlorine, 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 chlorine. Two, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. That was me counting the number of electrons. So I've used all the electrons. If we check formal charges, 5 valence electrons minus 0 dots and 5 lines, that's a 0. 7 valence electrons minus 6 dots in 1 line, that's a 0. So that's our correct Lewis structure. So let's look at the number of electron domains. 1, 2, 3, 4, 5. The electron domain geometry, since it's 5 electron domains, if we look at our chart, it is trigonal.
Hi, Mommy.
Hi, baby. Shh.
Hi, Mommy.
Hi.
Hi, Mommy.
Griffin. Can you be
Hi,
quiet for me?
Mommy.
I know. Can you be quiet for me?
Hi, Mommy.
Hi, baby.
And pause your stuff.
No, I'm doing stuff.
Hi, Mommy.
Hi, baby.
Hi, Mommy.
Griffin. Okay.
Yay.
So, trigonal bipyramidal. Go, baby. Go. Okay. Sorry. So, trigonal bipyramidal, how you can remember that with 5 is trigonal is 3 and bi is 2 and 3 plus 2 is 5. So, molecular shape. There are 5 bonding electron domains and 0 non-bonding.
Last night.
So 5 bonding, 0 non-bonding. The molecular shape is also trigonal bipyramidal. Bond angles, this is the weird one. There are 2 bond angles. Well, actually 3. 90 degrees, 120 degrees, and 180 degrees. This is the one that kind of looks like this. There's the 120 degree, there's the 90, and there's the 180. CH3 plus. Oops, nope, wrong. Carbon is 4. 3 hydrogens. And then it's going to be -1 because of the positive charge. Positive charges meaning they've lost an electron. So this only has 6 electrons. Carbon's in the middle. And I've actually used all 6 electrons so far. So that's my Lewis structure. Now it looks weird, but that's all I can do. Carbon has a positive formal charge and the hydrogens have 0 formal charges. So we knew that it wasn't going to be all zeros. So the number of electron domains, 3. The electron domain geometry is trigonal planar. And the molecular shape, well, there are 3 bonding, 0 non-bonding. So it is also trigonal planar. And the bond angles are 120 degrees. Okay. KRF2, so 8 for the krypton, 2 times 7, so 22 electrons. Kr is in the middle. I connected to fluorine. And fluorine, I've used 4 electrons. Filled the octet of the outside atoms. I've used 12. So I have 6 electrons left. So they have to go in the central atom. If we checked formal charges, fluorine, 7 valence electrons minus 6 dots in 1 line would have a 0 formal charge. Krypton is 8 valence electrons, 6 dots, and 2 lines, has 0 formal charge. This is just another one of those situations where the central atom breaks the octet rule. So the number of electron domains, what do you think that's going to be? 1, 2, 3, 4, 5. So its electron domain geometry is trigonal bipyramidal. Its molecular shape, well, it has 2 bonding and 3 non-bonding domains. Okay, so it's got 2 bonding and 3 non-bonding, which adds up together to be a total of 5, which is why this is trigonal bipyramidal, but its molecular shape is linear. And its bond angle then is just going to be 180 degrees. It's just a straight line. In this case, it actually looks just like this. It's a straight line. Okay. So you have to draw the Lewis structure first. You don't necessarily know what something's electron domain geometry, the number of electron domains it's going to have. Because if you just looked at this and you thought, oh, it's going to be Kr in the middle and attached to 2 fluorines, so it's going to have 2 electron domains, one fluorine and the other fluorine. We'd be super wrong. This actually has 5. This one you would have been lucky. This one you would have also been lucky. That one you would have been wrong because it has 4 electron domains. If you looked at that and saw, oh, it's 1 phosphorus and 3 fluorine, so it's got 3 electron domains. You have to draw the Lewis structure. Would have been wrong on that one also. So there's just nothing to say other than you have to draw the Lewis structure first. Sometimes I'm going to give you the Lewis structure and then ask questions about them. But there are times that you might be expected to have to draw them and then answer questions about them. So if we've got a big molecule, something like this, you would never be expected to draw a molecule like this. This is what you learn how to do in organic chemistry. We are not in organic chemistry right now. But I could draw a molecule for you like this. There's not a shape for this giant molecule. There's not like a special shape as they get bigger. Instead, what we do is we treat the atoms inside of it as kind of small central atoms. So like this would be atom 1, atom 2, atom 3. And what we can do is we can look at each of those atoms and figure out the number of electron domains they have, their electron domain geometry, their molecular shape, and their bond angle. So if we just look at this carbon right here, and we just look at the things directly touching it, there are 1, 2, 3, 4, I'm going to put atom, so 4 electron domains. So it would be the tetrahedral electron domain geometry. It has 4 bonding and 0 non-bonding electron domains. So it would be tetrahedral molecular shape, and it would have a bond angle of 109.5. Atom 2, if I'm just looking at this carbon and the things touching it, there's 1, 2, 3 electron domains. Trigonal planar is the electron domain geometry. Trigonal planar is the molecular shape. And the bond angle would be about 120 degrees. It would be a little distorted because there's a double bond, but it would still be about 120 degrees. Atom number 3, the oxygen. It's got 1, 2, 3, 4 electron domains. So it's tetrahedral electron domain geometry, but its molecular shape is bent because it has 2 bonding and 2 non-bonding, and its bond angle is less than 109.5. So what I'm going to do is give you a big molecule like this that I have drawn, and then ask you questions about individual atoms. So something like, because what actually happens if you see this, this is the one we said was tetrahedral. Well, if you look at this, that's actually tetrahedral. That's what the shape looks like. This one we said is trigonal planar. Well, look, it looks like a trigonal planar. And this one is bent. So in real life, each of these atoms has their own shape, and they just happen to be attached to each other. This one down here is just the space filling model. It's computer generated, just showing how big the atoms actually are. In real life, atoms aren't connected by sticks. That's just like the models that we use. So here's an example of a structure that I've already drawn, and I'm going to have us answer questions about the numbered atoms. So carbon, number 1. 4 electron domains. It's got a tetrahedral electron domain geometry, a tetrahedral molecular shape, and a 109.5 degree bond angle. Why don't you take a second, hit pause on this, decide what you think for number 2, number 3, and number 4, what their number of electron domains, their electron domain geometry, their molecular shape, and their bond angle. So hit pause, try those, and when you're finished, hit play again, and then we'll check our answers. Okay, so number 2, 3 electron domains, trigonal planar, electron domain geometry, trigonal planar, molecular shape, 120 degree bond angle. Number 3, 4 electron domains, tetrahedral electron domain geometry. It's going to be trigonal pyramid, molecular shape, 3 bonding, 1 non-bonding, and a less than 109.5 degree bond angle. Number 4, 4 electron domains. So it's tetrahedral electron domain geometry. Its molecular shape is going to be bent, 2 bonding, 2 non-bonding, and its bond angle is less than 109.5 degrees. I could have made this like atom 5 or something, but I didn't. So I would give you I would have to draw the structure, and then I would point out the atoms that I want you to do. We're going to do one more example, and then we'll be done with this video. So here's another really big one. Oh, I just realized there's a mistake on this one. That shouldn't be there. So the thing that's in purple, that's just like blank space as far as you're concerned. Okay, so 1, 2, 3, 4, 5. We're going to do all 5 of these. So carbon 1, this one, with the purple being gone, has 3 electron domains, trigonoplanar, electron domain geometry, trigonoplanar molecular shape, 120 degree bond angle. Carbon number 2 is actually exactly the same. 3 electron domains, trigonoplanar electron domain geometry, trigonoplanar molecular shape, 120 degree bond angle. Carbon number 3 has 2 electron domains. So it's got a linear electron domain geometry and a linear molecular shape, and 180 degrees is the bond angle. Carbon number 4 has 3 electron domains. It's trigonoplanar for both the molecular shape and the electron domain geometry, and 120 degree bond angle. I don't know where that line came from. Nope. There. And then atom number 5, the nitrogen, has 3 electron domains. It's trigonoplanar electron domain geometry, but it is bent molecular shape. It has 2 bonding, 1 non-bonding electron domain, and its bond angle is less than 120 degrees. So this video was just letting us practice taking Lewis structures and applying this VSEPR theory to figure out the number of electron domains, figuring out the electron domain geometry, figuring out the molecular shape, and the bond angles. These big molecules you would not be expected to draw, but the examples that we did that I did draw, those are the types of things that you need to be prepared to draw yourself and then answer questions about.